Infinity, a concept that has captivated mathematicians, philosophers, and dreamers for millennia. It stretches our imagination, defies intuition, and beckons us to explore its enigmatic depths. What does it mean for something to be truly infinite? Can we ever grasp the boundless nature of the universe or the endless possibilities that lie before us? In the realm of mathematics, infinity is not merely a philosophical musing, it is a powerful tool. It allows us to explore the limits of logic, delve into the structure of reality, and uncover hidden truths about the nature of existence. And at the heart of this mathematical exploration lies a fascinating and mind-boggling concept, the Löwenheim-Skolem Theorem. This theorem, with its deceptively simple premise, has profound implications for our understanding of infinity, logic, and the very fabric of reality. It challenges our intuition, shakes the foundations of our mathematical certainty, and leaves us in awe of the vastness and strangeness of the universe we inhabit. Prepare to embark on a journey into the heart of infinity, where logic reigns supreme and surprises await at every turn. To understand the profound implications of the Löwenheim-Skolem Theorem, we must first delve into the language of mathematics itself, logic. Logic, in its purest form, is the study of valid reasoning. It provides us with a framework to construct arguments, analyze relationships, and determine the truth or falsehood of statements. At the heart of mathematical logic lies a system called first-order logic. This system allows us to express statements about objects, their properties, and the relationships between them. For instance, we can use first-order logic to express the statement, all stars are giant balls of plasma. Here, stars and giant balls of plasma are objects, and all and are represent relationships between them. First-order logic is incredibly powerful because it allows us to create complex statements about the world around us and then analyze their validity. It forms the bedrock of mathematics, computer science, and many other fields that rely on rigorous reasoning and deduction. It is within this realm of first-order logic that the Löwenheim-Skolem Theorem emerges, shaking our understanding of infinity to its core. Imagine building a magnificent castle. Every detail is perfect, from the soaring towers to the intricate mosaics. You believe this castle to be unique, a testament to your singular vision. Now imagine discovering that a smaller, seemingly insignificant replica of your castle exists. Every detail is faithfully reproduced, just on a smaller scale. This, in essence, is the unsettling revelation of the Löwenheim-Skolem Theorem. This theorem, named after mathematicians Leopold Löwenheim and Thoralf Skolem, states that if a set of statements in first-order logic has an infinite model, it must also have a countable model. In simpler terms, if your logical system can describe an infinitely large structure, it can also describe a smaller, countable version of that structure. This theorem has two main parts, the downward Löwenheim-Skolem theorem and the upward Löwenheim-Skolem theorem. Both have mind-boggling implications for our understanding of infinity and the limits of logical systems. Section 4. Downward Löwenheim-Skolem, Shrinking Infinity, Expanding Perspectives. The downward Löwenheim-Skolem theorem states that if a set of statements in first-order logic has an infinite model, it must also have a countable model. This means that even if our logical system can describe an uncountably infinite structure, such as the set of all real numbers, there must also be a way to describe a smaller, countable version of that structure using the same logic. Imagine the real number line stretching infinitely in both directions, containing every possible decimal representation. The downward Löwenheim-Skolem theorem tells us that there's a way to pick out a countable subset of these real numbers, forming a miniature version of the entire number line, while still satisfying all the rules of our logical system. This is akin to finding a perfectly formed snowflake that, despite its finite size, reflects the intricate beauty and complexity of an entire blizzard. This concept challenges our intuition about the nature of infinity. If our logical system can't distinguish between an uncountably infinite structure and a smaller countable one, what does this tell us about the limits of our ability to truly grasp the concept of infinity? Section 5. Upward Löwenheim-Skolem, The Unfathomable Vastness of the Uncountable. The upward Löwenheim-Skolem theorem takes us in the opposite direction. It states that if a set of statements has an infinite model of a certain size, it also has infinite models of all larger infinite sizes. This means that our logical systems, even when describing seemingly small infinite structures, are capable of encompassing vastly larger infinities. Imagine a vast library containing every possible book that could ever be written. The upward Löwenheim-Skolem Theorem tells us that there are even larger libraries, containing not only all the books in our original library, but also an unfathomable number of additional books representing even larger infinities. This concept highlights the truly awe-inspiring nature of infinity. There is no largest infinity. Every infinite set is dwarfed by even larger ones, stretching our imagination to its very limits. It's like peering through a telescope and realizing that every galaxy we discover is just a tiny speck in an even vaster, more awe-inspiring cosmos.